Okay then, so as Debbie said, in my part of the talk, I'm going to describe some of the different component network meta-analyses models that have been put forward for analysing components of interventions, and illustrate with some examples where these methods have been used in practice. So the first example that I'm going to be working with is the one that Debbie's already introduced to you. So this was based on a piece of work which updated a Cochrane review that had looked at psychological interventions for patients who had recently undergone, had recently had an MI. There were a range of different outcomes that were reported in this review, some of which were binary outcomes like mortality and whether or not a non-fatal MI occurred in the future. But many were continuous outcomes such as depression, anxiety. We're focusing on depression here. But the methods that I'm going to show to you can be applied regardless of whether the outcome is binary or continuous or perhaps another outcome measure. If your outcomes are binary, then the models assume that the data has been generated using a binomial distribution, and the statistical model is put on the log odds ratio scale. So we estimate log odds ratios. I'm calling these delta IK, so that's sort of, you can think of that as the treatment effect, where I is the study number, so study I, and K is the arm of that trial. So K doesn't represent the intervention, it represents the arm, and that might be a different intervention. So arm 2 would be different interventions in different studies. Each of these are relative, these treatment effects are relative to whatever was in arm 1 of that particular study. And again, what could have been in arm 1 might have been different in different studies. When we have continuous outcomes, then instead of assuming the data has been generated by a binomial process, we instead assume it's been generated using a normal distribution. And the treatment effect, the delta IK in study I and arm K, is, instead of being a log odds ratio, it's a mean difference, or potentially a standardized mean difference. And for the depression example, that's what the outcomes represented, standardized mean differences. Okay, so the network meta-analysis model looks like this, and this is very similar to what Debbie showed you on her slide. The treatment effect that we're modeling, the delta in study I on arm K, which could be a log odds ratio, a mean difference, or a standardized mean difference, whichever that is on the left-hand side, that is assumed for a fixed effect model to be equal to the effect of the intervention that was given on arm K of study I, take away the effect of the intervention that was given on arm 1 of study I. So the effects D are all relative to a reference treatment. So in the depression example, that would be usual care. So our reference intervention is usual care. So each D represents the effect of each of the different interventions compared with usual care. And so if we had a study which compared an active intervention compared with usual care, then this expression would be the treatment effect of that active intervention compared with usual care minus, and actually it would be minus nothing, because usual care compared with usual care cancels out and it's just 0. But if we had a study which compared 2 active interventions, then it would pick out the difference between the effects on those 2 active interventions. And that's how network meta-analysis works. It makes sure we always pick out the right comparison of intervention comparisons that have been conducted on each study. The random effects model looks exactly the same, except we assume that the study effects for each treatment arm and study are not exactly the same as each other across studies, but similar. And there's some between study variability, which we've called tau here. Tau squared is the between study variance. And so each study estimates something a bit different to each other, but they're centered around the same central point, which is the difference. I don't have a pointer on here. Well, do I have a pointer? No, I don't have a pointer, sorry. Oh yes, you can see it now. Okay, my mouse. So the where this distribution is centered is exactly the same as the expression up here for the fixed effect model, but we've got a between study variance parameter here. Okay, and our component network meta-analysis models are given to these D parameters. So that's the treatment effect of a given intervention compared with usual care. In the depression example, the psychological interventions example that we've been working with, as Debbie described, we classified the components of each intervention as usual care, educational, behavioural, cognitive, relaxation or support. So, for example, we might have had an education plus cognitive plus relaxation intervention, or an educational plus behavioural intervention. There are 32 possible combinations of all of these interventions. In the full data set, 19 out of those 32 were included in at least one study. If we just focus on the depression outcome, then 10 out of the 32 possible combinations have been included in the RCTs. So the four models I'm going to describe to you, well, Debbie's already described the first and the bottom one. So the first one is where we lump all of those interventions together as if they were just a single comparator, and that's certainly historically what would have been done when we have interventions like this. They just get lumped together and assumed to be the same thing. The next level of complexity is to try and tease that out by adding, having a different effect for each of the components within that intervention. So on the previous slide, an edu plus cog plus relax intervention would be the sum of its parts, the educational effect plus the cognitive effect plus the relaxation effect. That assumes that there are no interactions between those components. But of course, there could be interactions. It could be that when you give two things together, they do particularly well. They have a sort of synergistic effect. Or perhaps when you've given one sort of an intervention with one component, adding another component which may be doing something similar doesn't give as much additional benefit because there's already something a bit like it in there. So there could be sort of antagonistic effects where the interactions are negative. And the most complex model that we could fit would be a full interaction model where every different combination of components is considered to be a distinct treatment. And Debbie showed you the picture of the network, and that's like having a network meta-analysis where each combination is considered separately. And the problem with that tends to be that we have very imprecise estimates. Okay, so mathematically, how would we write down these four different models? So in the first one, where we assume all of the effects are sort of lumped together, then our model is essentially saying that the intervention effect is equal to, the Ds are equal to an effect of psychological interventions in general, as long as the intervention is a psychological intervention. If it is usual care, then we set this equal to 0. So essentially all treatment intervention effects are considered to be the same, and it's just the same effect of a psychological intervention compared with usual care. This is exactly the same thing that would be done in a standard pairwise meta-analysis. And it answers the question, which is a useful question, are psychological interventions in general effective compared with usual care? And that's a question we might be interested in. So I think this model has value, although the worry that we have is that because we've lumped all these very different interventions together and assume that they're having the same effect, that could be introducing quite a high level of heterogeneity. The next model that we can look at is an additive main effects model. So here we assume that the intervention effect is equal to a sum of its parts. So we would have an effect of educational interventions, and this I notation here is saying, well, we'd include this term if the intervention included an educational component, and it wouldn't include this if it didn't. Plus the effect of behavioural interventions times an indicator to say whether or not that intervention included a behaviour component or not, and so on. So, for example, if our intervention had behavioural and cognitive components, then the effect of that intervention would be the sum of the behavioural component effect plus the cognitive component effect. And this model allows us to answer a slightly more refined question. It can help us answer are psychological interventions that contain a particular component effective compared with interventions that don't have that component, as long as all other things are equal. So the adding educational component would be assumed to be the same regardless of whether the other intervention had behavioural or cognitive or support, for example. And another nice thing about this model is it's easy to estimate all of these. It's easier to estimate all of these parameters than it is to estimate that full split interaction model where we treat each combination as different, because we've got slightly better estimating power. We've got more studies contributing to these estimates. It also means that we can make predictions, as long as we're happy with the effect, the assumption that there's no interaction. We can make predictions for any combination by just adding together their component parts. Now, that means that we can make predictions for combinations that weren't actually included in the data set. So let's say that none of our trials compared interventions that had relaxation plus behavioural plus support. We would be able to make an estimate, a prediction for that effect by just adding the beta relax plus beta behave plus beta support. So that's quite a powerful property of this model, but it does make an assumption that there's no interactions between the effects of these different components. We can relax that. By assuming interaction effects, and we can have a whole range of different complexities, two-way interactions, three-way interactions, and so on. In practice, it's very difficult to fit even a two-way interaction model, so I'm not going to show you more complex models. But a two-way interaction model would look like this. We'd have those same main effects that we had on the last slide, the component effects for education, behaviour, cognitive, and so on. But then we'd add on these extra effects. So I've got an effect for having education and behaviour together in interventions that include both education and behaviour, plus an effect for education and cognitive together for those interventions that have education and cognitive components, and so on. And I haven't written them all out here because you can imagine there's a lot of these interaction effects to estimate. And you can start to see quite easily, I think, that this model is going to be difficult to estimate because we've got so many parameters that we have to estimate. For an example, if we had an intervention that had a behavioural and a cognitive component, then the treatment effect for that intervention would be beta behave, beta cog, plus, because we now have the interaction as well, we have to also have beta behave cog. So this additional interaction term, if it's positive, will mean that giving these two things together has an over and above effect than you would expect if you just had the effect of behavioural interventions on their own and the effect of cognitive interventions on their own. If it was negative, then it would suggest that they have an antagonistic effect. So this model can answer the question, are psychological interventions that contain specific pairs of components effective, everything else being equal? The full interaction model is where we assume that each intervention has its own effect regardless. We don't allow any modelling of the components at all. We just assume every intervention has a separate effect. And that is equivalent to a standard network meta-analysis where each of the combinations of components is treated as separate treatment. And this answers the question, are psychological interventions with a particular combination of components effective compared to usual care? Which is a nice question to be able to answer, but it's only possible to answer this for the combinations that have been included in the RCTs. So for the depression example, that would only have 10 out of the 32 potential combinations that we could get estimates for. So the generalizability of the findings is less good. And this is just showing that graph that Debbie showed earlier, just showing you just how many of these we wouldn't be able to get estimates for. So as an overview, as we go from the single effect, the lumped effect, all the way down to the full interaction effect, the models get more complicated, they get harder to estimate, but on the other hand, they make less strong assumptions, they become less generalizable, and the estimates get less precise, to the extent that very often you can't fit some of these more complicated models. How do we choose between them? Well, I always have a theory that I prefer simpler models. So I would rather be higher up this list of models than lower down it if possible. But on the other hand, I want to be able to choose a model which gives an adequate fit to my data and doesn't have a very high level of heterogeneity, which makes the interpretability of the model estimates complex. So I look at model fit statistics. I fitted these models in a Bayesian paradigm where the deviance and the deviance information criteria are methods to assess model fit. But these models can also be fitted in a frequentist paradigm. Goethe Rücker's got some routines in R which allow you to fit these models. And there you'd use frequentist statistical measures of model fit, which are analogous really to these. Another important thing to look at is heterogeneity. So the whole point really of wanting to model these interventions is because we believe that there's a lot of heterogeneity in complex interventions, and that our supposition is that by focusing on estimating different component parts, we might be reducing some of the heterogeneity compared with that lumped single effect model. So it's important to look at heterogeneity as well as model fit. And looking at the estimates or the intervals, confidence intervals or credible intervals around the estimated regression parameters is also useful, because obviously if that contains 0, then that suggests that we can't be confident that that there's a true effect. So if we look at the results that we get from the psychological interventions example, what I've put up here for each of the models, I've shown the deviance information criteria. Now we want this to be as small as possible, but differences of about 3 to 5 are not really that important, so differences bigger than that would be considered important. So what you see from this is really there's not an awful lot of difference between these different models in terms of their deviance information criteria. In terms of heterogeneity, the between study, so this should be tau there, I apologise. The between study standard deviation is 0.19. If we lump everything together, it's 0.19 if we separate things into their component parts. So the heterogeneity hasn't been reduced by going from the lumped model to the main effects in this example. It does reduce if we go to higher order interaction models, suggesting perhaps there's some higher levels of interaction. However, if you look at the estimates of those interaction parameters, they're all very uncertain with very wide confidence intervals around those effects, and they all contain 0. So although it looks like there could potentially be some extra heterogeneity that's being explained by those higher order interaction models, we're not getting useful results from those models. And that's really, as you saw in that picture, that there's actually very sparse evidence to be able to estimate them. If we just look at the lumped effect, we see that there's an overall standardized mean difference of -0.23, suggesting these interventions are effective for reducing depression following myocardial infarction. And if you look at the confidence interval around that, that's very much less than 0, suggesting that this effect is a meaningful effect. Well, not meaningful, but statistically significant. If we look at the main effects model, this is adding the additive component models, then we can see that there seems to be some indication that interventions that include a behavioural component may be those that are most effective, and similarly those that have got a cognitive component. And because we assume an additive effect and that there are no interactions in this model, the effect of having both behavioural and cognitive component would be to take these two effects and add them together. So rather than being about -0.2, if you add those two things together, it'll be more like -0.4. Okay. So, sorry, just to sum up then, so we can conclude that yes, there seems to be evidence that that psychological interventions are effective. That's what the lumped model tells us, and we can see that, that interventions that have behavioural and cognitive components in particular might be especially important. There may be further interactions, but we need more detailed evidence to be able to explore that further. Okay, a couple of extra examples just to finish with, just to show you how these methods have been applied in practice. This is a HTA report looking at electronic aids for smoking cessation. So by that I don't mean e-cigarettes, I mean using electronic technology such as the internet or PC or mobile phone apps in order to help people, support people to stop smoking. The interventions were classified as a combination of either an electronic component and a non-electronic component. They were defined as this. So most interventions had some kind of electronic component, so that was either nothing, a single generic component, multiple generic components, single tailored components, or multiple, so a single tailored component plus a generic component, or multiple tailored components. And the non-electronic interventions, like the control conditions, were nothing, generic self-help material, brief advice, telephone or face-to-face counselling, pharmacotherapy, or counselling plus pharmacotherapy. You can see what the this is just showing you what the network of evidence, if we sort of look at all the different combinations of these interventions, and you can see, as for the previous example, not all combinations have been included in RCTs, but that doesn't prevent us from fitting some of these models with additive components. These are the results from fitting the single effect model 1, where we see that electronic components compared to control seem to be effective. This is a log odds ratio, and it shows that they reduce. Sorry, this is a log odds ratio. Apologies. So this shows. Apologies. This is an odds ratio showing that this reduces the effect of stopping smoking. I think it's the other way around. I apologize, I've just got totally mind blocked there, but I think that this shows that these are effective in reducing smoking, in stopping smoking. The electronic components, if we look at the different individual bits of the components, we see that that here, if an effect of 1 is no effect and values less than 1 are positive effects, showing that it's effective, then the interventions that have single tailored components or multiple tailored components seem to be the effective components of interventions, whereas there isn't any evidence particularly that the non-tailored, the generic components are important. So this is suggesting to us that yes, these types of interventions are effective, and the thing that's most important is that you use tailored components to these interventions, tailored to the individual. Though to note that the majority of the evidence was on those tailored formats, so it's possible that the other types, the non-tailored intervention types, may have been effective, but we simply didn't have enough evidence to have enough precision for those effects. So we can't conclude they're not necessarily effective, but that's not where the evidence was. It highlights that all of these models, they're really dependent on the availability of the data that we've got. Okay, another example briefly that we looked at is where we're looking at CBT interventions for patients, for adults with depression. This is the INTERACT study and it's published by Lopez. This is showing you the network meta-analysis plot for the evidence that we had available to us. The CBT is kind of the active interventions, and they were split into 3 different categories: those that were face-to-face, those that had multimedia and those that were a mixture, a hybrid between multimedia and face-to-face. If we look at the effects from that network meta-analysis, then we see that it seems, well, some interesting things here, in that waitlist seems to be detrimental, which I think has been shown in other studies as well. But in terms of CBT, all of these CBT interventions look to be effective. There's much more evidence on face-to-face CBT. Hybrid, there isn't very much evidence. And multimedia seems to be maybe a bit less effective than face-to-face CBT, which may be what you might expect. But we wanted to try and understand what aspects of these CBT interventions might have been driving these results. So we fitted a model which is very like the additive model that I showed you, except that we fitted an overall main effect for CBT, and then we looked at modifications to that for interventions that had multimedia, cognitive techniques, behavioural activation, psychoeducation, and so on, all these different components of what makes up potentially a CBT intervention. And what you can see from this is that you can see that multimedia is a bit on the positive side, which matches what we saw on the previous slide in that it isn't quite as effective as face-to-face CBT. But really none of these effects cross the line of no effect. So we didn't really get any, although we did, it was an amazing piece of work and we categorized everything very carefully, and it's a lot of statistical analysis. What we really found and concludes at the end of this is that CBT is effective, and we didn't really manage to go and say, well, one particular type of CBT is more effective than another. This is just to show you what the full interaction model would look like. And you can see there's a lot of comparisons that have been made here, and in fact it is possible to fit this model and you get estimates. But it's very imprecisely estimated. The scale of this graph is much wider than the scale of the previous graph I showed you because the uncertainty around these estimates is so big. So, in summary for that example, we saw that CBT interventions are effective, but we didn't really manage to find a particular set of combinations of components that were more effective than another. I think I'm running out of time. I've got one last final example I was going to just show you, just to show that these methods can be used not necessarily in pharmacological or psychological type interventions, but also in pharmacological interventions, where, for example, you have combination therapies. And just to note that this has been used in practice in NICE technology appraisal, in COPD, where you have combinations of different therapies, and it seemed from the evidence that additive models were reasonable. So if you look at the LABA effect and the ICS effect here, they add together to give you the combination therapy effect, and that supported the idea that we could use these that they could use these additive models in this technology appraisal. Okay, so just to sum up, I think component network meta-analysis models have potential to identify active ingredients of complex interventions. By fitting additive models in particular, I think these are the most feasible to fit in practice. They give us more precise estimates than a standard network meta-analysis. They can allow estimates to be obtained for combinations that haven't been included in the RCTs, but they do assume no interactions, which is very difficult to verify in practice because we generally don't have enough evidence. I think all of these methods are very limited in what they can achieve, and I think this talks to the question that we had earlier, in that I think we need very rich evidence sources to estimate these, just to estimate the additive models, let alone interaction effects. And so I think the methods, I think the methods are good, but I think using them in situations where there's very limited evidence means you're very unlikely to be able to identify effects. I think the sorts of studies which are useful, particularly useful, are these sort of dismantling studies where you get direct comparisons of having a component or not within the same RCT, and that gives a much stronger estimating power than where we're trying to make those inferences across RCTs rather than within them. And that's it. Thank you.
Oh, that's wonderful. Thank you very much, Nikki. We're at time. I'm just wondering if you're happy to stay on and just answer perhaps a few questions.
That's fine with me. Okay,
great. So the first question, I think, is a bit of a clarification or an interest question in one of the examples you presented. And does the example of psychological interventions and depression relate to a clinical or a subclinical population, or both?
Debbie, can you remind me what the population was in the? I think they were clinical populations.
Well, I think so. The population is people who've had a heart attack. I think it's likely that they are, in terms of their depressive symptoms, that there'll be a combination of both.
Yeah, sorry, in that one, but in the interactive example, they were definitely diagnosed.
Oh, is that? Yeah, it's not clear whether they mean in the first example or the interact, but interact is clinical. You're right, Nikki.
Okay, so the next question is around, I guess, assessing the certainty of the evidence and whether when you use these component models, how you go about assessing the certainty of the evidence.
So in terms of certainty, statistical certainty, that's what comes out of the modelling. So the credible intervals around the estimate give us an estimate of the statistical uncertainty. In terms of other, other issues that there may be with the evidence that may reduce our certainty. I mean, Debbie might be better to answer this one, but I mean, things like assessing the risks of bias in the studies and how generalizable it is and so on. I think that can be done in the same way as in any network meta-analysis, and in a way, by trying to explain some of the heterogeneity, we're trying to deal with that, I guess. Debbie, do you have anything to add to that?
No, just to say I completely agree with you that the if one is using a grade approach to assess the certainty, then you are still assessing the certainty at the study level and then looking across the body of evidence to summarise that. It wouldn't be that you'd start to look at the individual components and assess certainty of those, other than what Nikki described as around precision and generalisability, directness. That's what I was looking for, the grade terminology.
A question that I had was for Cochrane reviewers who are doing reviews where they have these complex interventions, do you think there's a preferable approach if they have some idea about for example, if they expect they're not going to have a large number of trials, would you suggest in that case that they may be much better to kind of go with the approach of fitting the additive model rather than the full model?
Yeah, so the approach I usually take is to build it up simply. So I think it's always good to try and fit the full model if you can, because you know that that's going to be making the least number of assumptions. The problem is that what you get out of that may not be very useful, may not be very generalizable, very imprecise, and so then I would I think fitting the additive model and the full models are the two models that I would generally try and fit in these situations.
Okay, and perhaps one last question is the question's from James Thomas, and he says that I guess up to a point that the more data the better in terms of being confident about the precision of estimates. Can you give any rule of thumb guidance re how many studies we should be looking for in order for this approach to work well?
I think that's a really good question, and I think it needs some simulation work, and it's something that I'm very keen to do, collaborate with as well. it isn't just how many studies. I don't think that's necessarily the issue. It's where those studies are and what comparisons they're making that's important. And so I think it's a much more complicated answer than just how many studies. I think it's all to do with the structure and the comparisons that are being made. My experience so far, I've just got empirical experiences, and my empirical experiences in practice, I think a lot of the time there isn't enough richness of the data, but I'd like to explore that further with simulation work.